Assalamualaikum and good day to everyone. Okay, now let us proceed with part 3 for chapter UV-Vis. We look at this diagram. It is the types of transition, and as we can see here, this line, the horizontal line here, represent the energy, the amount of energy levels. Okay, so the length of the arrow is proportional to the amount of energy needed to promote the electron between this energy level. Here we have 5 types of energy level, and this arrow represents the amount of energy needed for electron to promote the electron between this energy level. So if you have a bigger energy jump, for example, this sigma bonding to the anti-bonding sigma pi, you will absorb light with a higher frequency, which is the same as saying that you will absorb light with a lower wavelength. Now look at this table. It shows the chromophores, the example, the excitation, and also the lambda max. Alright, so what is the chromophore? It is the groups in a molecule which absorb light. So we call it as the chromophores. As we can see here, this is the C double bond C, which is unsaturated carbon. So for unsaturated, it is a pi, right? Pi to pi star anti-bonding, and also the triple carbon-carbon triple bond, which is pi to pi star. So we also have a CO carbonyl group, N to pi star, and also pi to pi star, and also the nitromethane. And for CX is lone pair, which is remember that a non-bonding orbital, N. Okay, N is for non-bonding orbital, is a lone pair on we can say that for oxygen, nitrogen, or halogen. The maximum absorption, we can see the value of the maximum absorption for each chromophore here. Chromophore is unsaturated organic functional group that absorb in the UV visible region. It contains electron with relatively low excitation energy, while also chromes is the groups of atoms such as OH, NH2, and halogen that attach to the double bond atom cause the normal chromophoric absorption to occur at longer wavelength or redshift. Now we look at the molecular absorption. The electronic transition do not occur in all the species when a radiation in UV region is passed through the sample. Generally, there are 3 types of species show the mentioned transition. These are inorganic, and complex form by charge transfer. So it is the same explanation as in the previous slide. So most absorption spectroscopy of organic compound is based on the transition of lone pair and pi electron to the pi star excited state. This is because the absorption peaks for this transition fall in an experimentally convenient region of the spectrum 200 to 700 nanometer. So this transition need an unsaturated group in the molecule to provide the pi electron. Molar absorptivities from N to pi star transition are relatively low and range from 10 to 100 liter mole per cm, and pi to pi star transition normally give molar absorptivities between 1000 and 10,000 liter per mole per cm. Okay, the effect of solvent. So if you use the UV visible spectroscopy, of course, you need to use the solvent. So the effect of the solvent for organic absorption, first we look at the blue shift, okay? Peak resulting from a lone pair to pi star transition are shifted to shorter wavelength with increasing the solvent polarity. So this arises from increases solvation of the lone pair, which lowers the energy of the n orbital. If we have a redshift, we want to scene for pi to pi star transition. Okay, so you need to look at the pi to pi star transition, what types of bond it absorbs. This is caused by attractive polarization forces between the solvent and the absorber, which lower the energy level of both the excited and unexcited state. This effect is greater for the excited state, and so the energy difference between the excited and unexcited state is slightly reduced, resulting in a small redshift. For inorganic absorption, many inorganic species show charge transfer absorption and are called charge transfer complex. For a complex to demonstrate charge transfer behavior, one of its components must have electron donating properties and another component must be able to accept electron. And absorption of radiation then involves the transfer of an electron from the donor to an orbital associated with the acceptor. The Woodward-Fieser rule, okay, which is the critical part in chapter 5, involve calculations of the chromophore. So Woodward and the Fieser is actually two different people, two scientists. It performed extensive studies of terpene and steroidal alkene and noted similar substituent and structural features. Wood predictable leads to an empirical prediction of the wavelength for the lowest energy pi to pi star electronic transition. So this wood was distilled by Scott in 1964 into an extensive treatise on the Woodward-Fieser rule in combination with comprehensive table and example. And a more modern interpretation was compiled by Rao in 1975. So this is some history about the Woodward-Fieser rules. So actually Woodward-Fieser rules, we use this rule uh, for the three specific chromophores, which are conjugated diene, conjugated dienone, and the aromatic compound. So basically, Woodward-Fieser rule, we can predict the wavelength of absorption maximum in UV spectrum and empirical prediction of the wavelength for the lowest energy pi to pi star, which involve the alkene, carbonyl, nitrile, and aromatic. And input used in the calculation are the type of chromophore present, the substituent on the chromophore, and shift due to the solvent. So basically, Woodward-Fieser rule, we want to determine the maximum absorption ataupun lambda max. Okay, if we want to predict it manually without the using of the instrument, we can approximately estimate by make our own calculation by referring to the table. Okay, for this chapter, for this subchapter, we will cover only conjugated diene and conjugated dienone. Okay. Now we look at the component in the Woodward-Fieser rule. Each type of diene or triene system is having a certain fixed value at which absorption takes place. This constitutes the base value or parent value.